Let us begin very gently. Tonight, or today, we will think about a classical method in statistical estimation called the method of moments. It has a name that can sound slightly formal, slightly old-fashioned, even a little mysterious at first. But the central idea is actually very simple and, in a quiet way, very natural. The method of moments is one of the first estimation methods many students meet in mathematical statistics. It is taught often because it gives us a constructive way to turn data into parameter estimates. It does not begin with a complicated optimization problem. It does not begin by asking what parameter makes the exact observed sample most likely. Instead, it begins with something more visible, more tangible, and in some ways more human. It begins by looking at the broad features of the data. When we look at a set of observations, we often notice certain summary characteristics before anything else. We notice the average level. We notice whether the values are tightly clustered or widely spread out. We may notice whether the distribution looks roughly balanced or whether it leans to one side with a longer tail in one direction. In ordinary language, we notice the center, the spread, and perhaps the asymmetry. These are not yet the full data. They are summaries. They are condensed descriptions. But they are often the first things our eyes and minds grasp. And the method of moments says, in essence, let us choose the model parameters so that the model has the same important summaries as the data. That is the whole spirit of the method. It is worth repeating. The method of moments chooses parameter values by making the model match the main visible features of the sample. If the data have a certain average, we ask the model to have that same average. If the data also have a certain variability, we ask the model to reproduce that as well. If we need to go further, we may also ask it to reflect some aspect of asymmetry or tail behavior. But the basic movement is always the same. Look at the summaries of the sample, look at the corresponding summaries of the model, and line them up. So the method is not trying, at least not directly, to fit every detail. It is not asking the model to explain every exact observed value in the most refined possible way. It is asking for something calmer and broader. Does the model, with the chosen parameters, resemble the data in its main structural features? There is a very useful physical analogy here. Imagine you are trying to fit a simple shape to an object, but you are not yet worried about every small curve or tiny irregularity. You begin with larger features. Where is the balance point? How wide is it? Perhaps how lopsided is it? Before attending to every detail, you match the center and the width. That already tells you a great deal. It gives you a first fit, a rough but meaningful alignment. The method of moments works in a similar spirit. It says, before worrying about every fine detail of plausibility, let us at least make sure the model has the right balance point and the right width. Let us make sure it captures the broad shape. And this is one reason it is taught so often. It is conceptually simple. Students can understand the goal without getting lost in technical machinery. It is often faster to derive than maximum likelihood estimation. And perhaps most importantly, it gives a first example of an estimation procedure that feels constructive. You are not merely told that an estimate exists. You can often build it with your own hands, step by step, by matching summaries. Let us pause and reflect on that. In statistics, many ideas become more manageable when we stop staring at raw data as a long list of numbers and start asking what the data are telling us in a summarized way. The average tells one story. The variability tells another. Skewness or asymmetry tells another. These summaries are sometimes called moments, and the method of moments gets its name from the fact that it uses such quantities as bridges between data and model. You do not need the technical language to understand the intuition. The intuition is enough. The model has characteristic fingerprints, and the data have visible fingerprints too. Match them. That phrase is worth keeping in mind, recognizable fingerprints of the data. Now let us make the idea more concrete. Suppose we have a model with just one unknown parameter. Then, very often, one summary of the data will be enough to estimate it. If the model says that the average level depends on that parameter, then we can simply force the model's average to equal the sample's average. The result is an estimate. If the model has two unknown parameters, then one summary is usually not enough. We need two pieces of information. So we might match the average and the variability, or the average and another suitable feature. In other words, if the model has more freedom, we need more summaries of the data to pin it down. This is a very natural principle. More unknowns require more information. The method of moments supplies that information through matched summaries. Now let us turn to a very classical example, the Poisson model. The Poisson model is used for count data. It is a model for things like the number of events in a time interval, the number of arrivals, the number of defects, the number of occurrences of something that can be counted. One of the reasons it is such a clean example is that it has just one parameter. So the method of moments has a very direct job. What is the broad feature of the data that matters most here? The typical count level. The average number of events. If the observed counts tend to be around 3, or 5, or 10, that average level already tells most of the story. So in the Poisson case, the method of moments says choose the parameter so that the model's typical count level matches the observed average count. And this feels immediately natural. If the data are counts and their averages, say, around 4, then it would feel strange to choose a model parameter suggesting a typical count of 1 or 10. The average count already contains the central signal. So the estimate that comes from matching the average feels not only mathematically convenient, but intuitively correct. This is one of the pleasures of the method of moments. In the right setting, the estimate feels like common sense made systematic. Let us say that again in a slightly different way. The Poisson example shows the method at its cleanest. The model has one main dial to turn. The data give us one very informative visible feature, namely the average count. So we turn the dial until the model's average lines up with the sample's average. At that point, the model is at least telling the same broad story about the level of count as the data themselves. There is something very restful about this. We are not chasing complexity. We are simply matching the most visible feature. Now let us move to a richer example, the gamma model. The gamma family is often used for positive data, especially data that are skewed and continuous. Here the situation is more interesting because there are typically two parameters. One influences overall scale, the rough size of the observations. Another influences shape, which is related to how concentrated or variable the values are and how asymmetric the distribution appears. So now one summary is not enough. Matching only the average would leave too much unresolved. Two different parameter choices might produce the same average while differing greatly in variability or shape. And that means we need a second summary from the data. A common choice is to use the center and the variability together. The average tells us about the general level. The variance, or spread, tells us how widely values fluctuate around that level. When we match both of these, we give the method enough information to estimate both parameters. This is an important moment to pause. With one-parameter models, the method of moments can feel almost automatic. With two-parameter models, we begin to see more clearly what the method is really doing. It is not performing magic. It is solving a matching problem. The data say, this is my center and this is my spread. The model says, for each possible parameter choice, I have my own center and spread. And the estimator is the parameter choice where those two descriptions agree. So in the gamma example, one parameter helps position the distribution on the positive axis, while the other helps determine how tightly or loosely it gathers around that position and how much skewness it carries. The sample center and sample variability taken together give us clues about both. This, again, is why the method feels intuitive. Instead of maximizing some abstract plausibility criterion, it asks the model to imitate the data's observable fingerprint. Not every fingerprint, but the main ones. It is worth repeating the phrase, the method of moments is the match the shape of the data method. Now, why is this method so widely taught, even though modern statistics often puts great emphasis on maximum likelihood and Bayesian methods? Part of the answer is educational. The method of moments helps students see estimation as something active and constructive. It teaches the idea that a probabilistic model implies certain summary features, and it teaches that data can be used to reverse that relationship. If parameters determine the summaries, then observed summaries can help us recover parameters. That is a deep and important idea. The model pushes forward from parameters to predicted features. Estimation pulls backward from observed features to parameter values. Another reason is practical. Sometimes the likelihood is awkward. Sometimes writing down the full likelihood is possible, but unpleasant. Sometimes solving the likelihood equations is hard. In such cases, the method of moments may give a quicker route to a usable estimate. It may not always be the most refined estimate. It may not always be the most statistically efficient. But it can be simple, transparent, and fast. And in some contexts, a quick approximate estimator is exactly what we need. For example, it can serve as a first pass. It can provide an initial estimate before applying a more refined iterative method. Or it can provide insight even when the final method will be something else. It tells us which features of the data are most directly linked to the parameters. Let us pause and reflect once more. The method of moments works especially nicely when the moments, or summaries, are easy to interpret. The mean is easy to understand. The variance is easy to understand. Sometimes high moments, related to symmetry or tail heaviness, can also be interpreted, though often less directly. When the summaries are meaningful and the model expresses them clearly in terms of parameters, the method feels elegant. But no method is perfect, and it is important to discuss the limitations calmly and honestly. One limitation is that matching only a few summaries may ignore important structure in the data. Two very different distributions can share the same mean and variance. So if we only match center and spread, we may miss differences in tail behavior, asymmetry, clustering, or other subtle features. The fitted model may agree with the data in broad terms while failing in more detailed ways. This is not a flaw unique to the method of moments, but it is especially visible here because the method openly restricts attention to selected summaries. It says, in effect, I will match these features and trust that they are the important ones. Sometimes that is wise. Sometimes it is too coarse. A second limitation is efficiency. In statistics, when we compare estimators, we often care not only about whether they are centered correctly on average, but also about how much they fluctuate from sample to sample. An estimator may be perfectly reasonable yet somewhat noisy. Another may extract more information from the same data and therefore vary less. This brings us naturally to the ideas of bias and variance. Bias asks whether a method tends to lean systematically too high or too low. If we could repeat the same sampling process many times, would the estimator, on average, overshoot the true parameter? Would it undershoot? Or would it land around the truth without systematic leaning? Variance asks how much the estimate wobbles from one sample to another. Even if it is centered well on average, does it bounce around a lot? Or is it relatively stable? These two ideas are worth stating again because they are so central. Bias is about systematic tilt. Variance is about instability across repeated samples. The method of moments can sometimes have noticeable bias, especially in small samples. And it can sometimes have larger variance than competing methods, especially maximum likelihood. In other words, it may lean a bit, or wobble a bit more than we would ideally like. But we should be gentle here. These are not reasons to dismiss the method. They are reasons to understand its role properly. It is often a first-pass estimator, a transparent estimator, a structurally meaningful estimator. It translates data summaries into parameter values in a direct and intelligible way. That has real value, especially in teaching, exploration, and quick analysis. Sometimes the matched summaries themselves do not behave especially well in small samples. A sample mean is often fairly stable, but other summaries may be more erratic. If the estimator relies heavily on a noisy summary, then the resulting parameter estimate may inherit that noise. So the performance of the method of moments depends partly on which summaries are chosen, and partly on how informative and stable those summaries are in the sample size we have. Now let us compare the method of moments to maximum likelihood estimation, because the contrast is illuminating. The method of moments asks, does the model resemble the data in its main features? Maximum likelihood asks, which parameter value makes the exact observed data most believable under the model? These are different philosophies. The method of moments is summary-based. It compresses the data into a few key descriptors and matches those. Maximum likelihood looks more directly at the full observed sample and asks which parameter value gives the strongest support to what was actually seen. So one method says, match the fingerprint. The other says, explain the exact pattern as convincingly as possible. Neither description should be taken too rigidly, but the contrast is helpful. The method of moments is often simpler to derive. Maximum likelihood is often more refined and often more efficient, especially in large samples, but it may be harder to solve or interpret initially. For a student meeting estimation for the first time, the method of moments can feel like a welcoming doorway. It teaches the logic of connecting model characteristics to data characteristics. Once that bridge is understood, maximum likelihood becomes easier to appreciate as a different, often stronger, but sometimes more technically demanding strategy. It is worth repeating this practical takeaway. The method of moments is often a simpler first pass. Maximum likelihood is often more refined, but not always easier to understand. That is a very balanced way to remember the relationship. Now let us gather the whole picture slowly. We begin with the idea that data have visible summary features: average, level, spread, asymmetry. We then notice that statistical models also have their own characteristic summaries, determined by their parameters. The method of moments builds an estimate by forcing agreement between those two wells. It makes the model summaries line up with the sample's summaries. In the Poisson case, the average count already carries most of the story, so matching the average gives a natural estimate. In the gamma case, we need at least two summaries because there are two parameters, and center together with variability helps identify them. Along the way, we saw why the method feels intuitive. It matches recognizable fingerprints rather than maximizing a global plausibility measure. We also saw why it is so often taught. It is conceptually clear, often quicker to derive, and educationally powerful as a first constructive method. And we also acknowledged the limitations. Matching a few summaries may miss important structure. The estimators may be less efficient than maximum likelihood estimators. Small sample behavior can sometimes be awkward. Bias and variance remain essential questions. Let us pause and reflect one final time. When you first learn statistics, estimation can seem like an act of mystery. How can one move from noisy data to a hidden parameter? The method of moments gives one calm answer. Look for stable, visible features. Ask how the model expresses those features. Then choose the parameter values that make the two agree. It is a method of alignment. It is a method of correspondence. It is a method of matching shape. And that is perhaps the best way to carry it in memory. The method of moments is to match the shape of the data method. Not the full shape in every microscopic detail, but the broad shape, the balance point, the width, sometimes the asymmetry, the leading structural traits. So when you hear the name again, you do not need to think first of formal definitions. You can think of a model and a sample being brought into agreement at the level of the main features. You can think of adjusting the model until its center and spread resemble the center and spread of the data. You can think of a first fit, a constructive fit, a feature matching fit. And in that sense, the method has a quiet elegance. It does not claim to do everything. It does something simpler. It says, let the model reflect what is most visibly true in the data. And that is a very good place to begin. So let us end with a slow, unifying summary. The method of moments is an estimation method built on summaries. Data have visible summaries such as average, level, spread, and sometimes asymmetry. Models also have summaries determined by their parameters. The method chooses parameter values so that these summaries agree. In a one-parameter model like the Poisson, matching the average may be enough. In a two-parameter model like the gamma, center and variability together may guide the fit. The method is taught often because it is simple, constructive, and intuitive. It gives a first way to estimate without needing the full machinery of more refined methods. At the same time, it may overlook structure, and its estimators may wobble more or lean more than alternatives such as maximum likelihood. Still, as a first pass, as a conceptual tool, and as a way of seeing how data and models speak to one another, it remains deeply valuable. And perhaps the most peaceful way to remember it is this: the method of moments asks the model to match the main visible features of the data. It matches the fingerprints. It matches the balance point and the width. It matches the shape gently before worrying about every detail.